This first part you can just pretty much read, but I highly recommend that you look at the diagrams in your textbook as well. So we're going to look at two types of calorimeters. So if you think of this, it's a calorimeter, so it's actually looking at something that measures heat. So there's a constant pressure one, which is one that is exposed to air. So we're going to use a really fancy one. It's going to be a styrofoam coffee cup type system. And again, this isn't effective for reactions that produce gases or high temperatures, but for the basic stuff we're going to do, it'll work fine. And the heat of reaction that we're going to be doing later is also going to be measured in this type of calorimeter. A bomb calorimeter is a very expensive device, and just what it sounds like is it has to be able to hold a high pressure or it will explode. So the pressure varies and the volume is constant. There's a picture of one on page 203. I don't have one in the lab area. It's used to measure calorie content of foods and heats of reaction, so you'll probably find a bomb calorimeter in the food lab at Snyder's of Hanover and at Oats Quality Foods. And then it's just a note here that I need to talk about with your textbook. They use delta U. I have never seen that in any other textbook, so you won't see that on the exam as well. So every time you see delta U, you're just going to refer to that as delta H. So delta means change, H is going to be heat, so think of it as change in heat. So the components of the calorimeter absorb heat. So heat capacity must be determined by burning a substance of known heat capacity. So our known substance is going to be benzoic acid. We have 1 gram of that, and that is going to evolve 26.42 kilograms of heat when combusted. So if 1 gram of benzoic acid is burned in a calorimeter containing 1.95 kilograms of water, we know that the heat lost by the benzoic acid and the bomb together should add up. So what that looks like in form is the heat lost by the benzoic acid is going to equal the heat gained by the calorimeter plus the heat gained by the water. So 26.42 kilojoules is coming from the knowing we have 1 gram of it. It's going to be the heat capacity of the calorimeter times how much it changes temperature, and it's going to change the same temperature as the water because they're in contact with each other. And then the cm delta T for the water is given here. So notice I did kilojoules per kilogram, so you can do joules per gram or kilojoules per kilogram. So as long as you're doing the same change with each top and bottom, you're okay with modifying that. Times my 1.95 times my 2.34 degrees Celsius, which is my temperature change of my water. So when we simplify that, we get the 26.42 kilojoules to just come down. I moved the number in front of the variable so you're used to 2x, not x times 2. So the 2.34 degrees Celsius times our variable, which is the heat capacity of the calorimeter, and just simplifying all of this, canceling my units, gives me my 4.45 kilojoules. So now I just need to move the 4.45 kilojoules over to the other side and get my like terms together and solve for the calorimeter value. So moving the 4.45 to the other side gives me 21.97 kilojoules and equal to 2.34 degrees Celsius times our variable. And then I just need to divide both sides by 2.34. And again, if you don't need to show all these algebra steps, that's fine. I just wanted to show you all of it. And that gives us a final value of the heat capacity of the calorimeter is 9.39 kilojoules per degree Celsius. So that means for every degree Celsius that it changes, you have to put 9.39 kilojoules into it. The amount of material for the calorimeter is not specified in the next problem. The amount of water has to be the same, and that's typically how a bomb calorimeter is used. But they have to give you the amount of water in the problem if it's not a continuum like this problem is. So calculating the heat of reaction using the calibrated bomb is actually 2 questions in one. So this all here is 1 question. And I'm going to show you 2 different things with this one. So if I want to know the heat of reaction, and that's going to be delta H reaction, I need to know the heat of my calorimeter times its change in temperature plus my water and its change in temperature. So I'm going to use my 9.39 from the last chapter, or excuse me, last question. And our temperature increases 7.3 degrees Celsius. And then I'm going to use the same thing I did for my water. Kilojoules per kilogram degrees Celsius times 1.95 kilograms times 7.3 degrees Celsius. Again, I'm just canceling my units. So when you add that all together, you get 68 kilojoules plus, or multiply all that together, 14 kilojoules, which is a total of 82 kilojoules. Now, you can go into, since we know we have a 1.5 gram sample, you can do 82 kilojoules divided by 8.2 grams. Oh, excuse me. About 1.5 grams. And that gives you a heat of 55 kilojoules per gram of methane. Okay, the second question, which I've underlined in yellow here, is going to be set up exactly the same way. I'm going to do one different step at the end, but just so you don't have to watch me write all of this, you're going to see it all flash on the screen, so be ready to pause. So you'll see they use the same 9.39 kilojoules per degree Celsius, which is the heat capacity of my calorimeter. The temperature change came from the problem here. I'm using the specific heat of water again, and the 1.95, which is the constant volume for this calorimeter, and the same temperature change for the water. Again, whatever the temperature change is the same for both objects since they are in contact with each other. Okay, when you calculate these out, you get 134 kilojoules. So notice there's 3 sig figs here because there's 3 in the temperature. The last one only had 2 sig figs because there was a smaller temperature change of only 2 place values. So the bigger the temperature change, the more sig figs you usually can keep. So it's a key to designing them to try and get larger values. Okay, when I sum those together, I need to be mindful of addition rule. I can only go to the ones place value, so this is 162 kilojoules. Now the 162 doesn't take into account our sample size of 1.15. Most of the time heats of reactions are given per mole, not per gram. So since we know that this is hydrogen and you would readily know the formula for that one, we're going to set this up to get kilojoules per mole. So that means I need to divide by my mass, which is 1.15 grams. That's given in the problem again. And I'm going to use the molar mass of hydrogen. Remember, it's diatomic, so it's 2.02 for every 1 mole. And then that will give me a final answer of 284 kilojoules per mole.